Right now, there is a single building in a small Dutch town that, if it disappeared tomorrow, would effectively freeze the progress of human civilization. We're not talking about a central bank or a government or an oil giant. We're talking about ASML, a company with a total global monopoly over the most complex machines ever built by humans. Machines so precise they use molten tin and high-energy lasers to print patterns smaller than a virus. Without these machines, there is no artificial intelligence, no next-generation smartphones, no cutting-edge military hardware. And here's the most shocking part. For decades, the world's smartest engineers believed the technology ASML was building was physically impossible. ASML is a Dutch multinational and the most important supplier in the semiconductor industry you've probably never heard of. They specialize in photolithography, the process of using light to etch microscopic patterns onto silicon wafers. This process is what turns sand into brains. Today, ASML is the only company on Earth capable of producing extreme ultraviolet lithography machines, or EUV. Each machine costs over $200 million. The next generation is already pushing $400 million. To understand how a niche firm from the Netherlands became the gatekeeper of the digital age, we have to go back to an unlikely beginning. A leaky wooden shed, and a gamble that almost destroyed the company. The ASML story begins in 1984 as a desperate joint venture between two Dutch firms, Philips, an electronics giant, and ASM International, a specialized equipment maker. At the time, Philips was a global powerhouse, but its chip-making equipment division was an afterthought, underfunded, overlooked, and constantly fighting deadlines. ASML's origin story has since become legend. A team of just 47 engineers, working out of a leaky shed next to a Philips office in Eindhoven. No market access, no brand recognition, and technology that needed to be rebuilt from scratch. In an industry dominated by Japanese titans like Nikon and Canon, ASML was the runt of the litter, and it showed. By 1988, ASM International pulled out. The investment wasn't paying off. Philips, dealing with its own cost-cutting crisis, came dangerously close to shutting the project down entirely. Internally, ASML was described as a cash-devouring experiment. The company was weeks away from extinction. The only thing that saved it was one final lifeline from Philips and a breakthrough. In 1991, ASML released the PAS5500 platform. It delivered better productivity, better resolution, and most importantly, real customers. For the first time, ASML turned a profit. By 1995, it was strong enough to go public. But inside the company, the leadership already knew something was wrong. They were winning, but they were about to hit a wall, because conventional light was becoming too thick, too blunt, to etch the ever-shrinking transistors demanded by Moore's law. To survive, ASML needed a completely new kind of light, a light source no one had ever successfully manufactured, one that would take 20 years, billions of dollars, and a belief that physics itself could be bent. ASML had survived its birth, but to own the future, they would have to create a light source that doesn't naturally exist on Earth. To keep transistors shrinking, ASML had to abandon conventional light entirely. They turned to extreme ultraviolet, or EUV. This light has a wavelength of just 13.5 nanometers. That's about 1/10,000th the width of a human hair, roughly the size of 5 DNA strands laid side by side. But EUV comes with a brutal problem. It's so fragile that it gets absorbed by almost everything, including the air you're breathing right now. So ASML was forced to redesign the entire lithography system to operate in a near-perfect vacuum. Inside the machine, microscopic droplets of molten tin are fired through a vacuum 50,000 droplets every second. A high-power CO2 laser, originally designed to weld cars, hits each droplet twice. The first pulse flattens the droplet into a tiny pancake. The second pulse vaporizes it into a plasma hotter than the surface of the sun. That explosion releases EUV photons, and the precision required is absurd. The laser must hit a microscopic tin droplet, moving at high speed, with accuracy comparable to firing a laser from the moon and hitting a coin on Earth. Because EUV light is absorbed by glass, So ASML partnered with Carl Zeiss, a German optics firm, to build something entirely new. Mirrors. Not ordinary mirrors, but the flattest man-made surfaces in existence. If one of these mirrors were expanded to the size of Germany, the tallest bump on its surface would be less than 1/10 of a millimeter. At this point, ASML had done the impossible. They had mastered the physics. But physics was only half the battle. Because now, they had to assemble a 180-ton machine so delicate it could be destroyed by a single human skin cell. An ASML EUV machine is not a single tool. It's a 180-ton system made up of over 100,000 individual parts. That complexity turned ASML into something unusual. They aren't just a manufacturer. They are a system integrator. Nearly 90% of the components are outsourced to a vast global network of around 5,000 specialized suppliers. Zeiss handles the optics. Cymer builds the laser source, a company ASML eventually had to buy outright to protect the supply chain. Inside ASML, this process is described as a symphony of chaos and nervous tension. Assembly happens inside clean rooms that are 10,000 times cleaner than outside air. Engineers wear full bunny suits and pass through air showers, because a single dust particle just 52 nanometers wide, about the size of a small virus, can destroy the entire system. Every EUV machine is essentially custom-built for customers like TSMC, Intel, and Samsung. No two machines are exactly the same. Before delivery, each system must be qualified, a process that can take up to 18 months. Only then is the machine disassembled, packed into 40 shipping containers, and transported using 3 Boeing 747s and 20 trucks. This extreme complexity, combined with decades of R&D and billions of dollars in sunk cost, is why ASML has no competitors left. Nikon and Canon tried. They simply couldn't stay on the treadmill of Moore's Law, which left ASML with something unprecedented. A total monopoly over the most advanced chips on Earth. And that monopoly didn't just make ASML powerful, it turned the company into a strategic target in a new technological Cold War. In the 21st century, advanced semiconductors are the new oil, and ASML sits directly on top of the well. That reality has dragged the company into a high-stakes geopolitical battle between the United States and China. The U.S. government, worried about Beijing's military and artificial intelligence ambitions, identified ASML as a strategic choke point and applied pressure accordingly. In 2019, the Dutch government, under U.S. influence, cut off China from ASML's most advanced EUV machines, freezing it out of the future of chipmaking. Washington then tightened controls further in 2024, requiring special export licenses even for advanced DUV systems that are still critical to semiconductor scaling. China responded the only way it could, by trying to build its own EUV future from scratch. Under a state-led effort often called China's Manhattan Project for semiconductors, researchers coordinated by Huawei and overseen by the Central Science and Technology Commission have spent years trying to replicate what ASML and its partners perfected over decades. What was once theoretical has now materialized in a high-security lab in Shenzhen. Sources say China completed a prototype EUV lithography machine in early 2025 and is testing it, marking the first time a country outside the West has built a machine capable of generating extreme ultraviolet light. That milestone challenges long-held assumptions about the pace of China's progress. The prototype reportedly fills an entire factory floor and was assembled with help from former ASML engineers, some recruited with significant incentives and working under strict confidentiality, and by reverse engineering components salvaged from older EUV systems through secondary markets. However, the prototype remains far from a commercial product. It has not yet produced working chips and key bottlenecks, especially precision optics like the ultrafine mirrors supplied by Zeiss and the complex metrology systems that make EUV reliable. Western officials and analysts had previously estimated that China would need a decade or more to approach advanced commercial EUV technology. Recent developments have compressed that timeline, with government targets aiming for domestic chip production on China-made EUV tools by 2028 to 2030. This race underlines a stark reality. Semiconductor sovereignty has become a core strategic objective. ASML isn't just a company. It's the gatekeeper of the most advanced manufacturing capability on Earth. control ASML, and you control how fast nations can innovate in AI, computing, and defense. Control or replicate EUV, and you reshape the balance of technological power itself. ASML's monopoly didn't make them complacent. It made them move faster. Their next platform is called High-NA EUV, also known as the EXE system. These machines are even larger than current EUV tools, bigger than a double-decker bus. Shipping just one requires 7 Boeing 747s. High-NA stands for High Numerical Aperture. In simple terms, it means the machine can capture light at steeper angles. That single change unlocks something massive. Higher resolution. Earlier EUV systems hit a wall. To print smaller features, chipmakers had to rely on multiple patterning, printing the same layer again and again. That process is slow, expensive, and brutal on manufacturing yield. High-NA eliminates much of that complexity. Smaller features, fewer steps, lower cost per transistor. Each High-NA machine costs between $370 and $400 million. Intel received the first R&D system in late 2023. TSMC followed in late 2024. These machines will define the 2-nanometer era and beyond. And ASML isn't stopping there. Their roadmap already includes Hyper-NA systems, expected sometime between 2032 and 2035. At that point, we won't be fighting engineering limits. We'll be fighting physics itself. As transistors approach the size of atoms, ASML may be building the final wavelength of light humanity will ever need to print the future. Building these machines is not just engineering. It's constant pressure. Inside ASML's cleanrooms, perfection isn't a goal. It's a requirement. There is no room for trial and error. A single defective component from any one of their 5,000 suppliers can halt an entire production line. And when that happens, everything stops. ASML operates under a culture of zero defects. Not because it sounds impressive, but because failure isn't survivable at this scale. That tension is the hidden cost of being the only company on Earth that can do this job. And the pressure doesn't end at delivery. ASML's machines are the designed bottleneck of every advanced semiconductor factory. If one EUV system goes down, a multi-billion-dollar fab comes to a standstill. Losses can reach millions of dollars per hour. That's why ASML maintains 24/7 on-site support across 16 countries, with engineers permanently embedded inside customer fabs. Because when ASML's machines stop, the world's most advanced technology stops with them. ASML's journey from a leaky Dutch shed to a $345 billion tech superpower shows how extreme specialization and long-term conviction can reshape an entire industry. By betting the entire company on a technology others believed was impossible, ASML didn't just win a market. They created a global bottleneck that is almost impossible to bypass. They are the silent integrators behind modern computing, coordinating thousands of suppliers to keep Moore's Law alive. Today, ASML isn't just Europe's most valuable tech company. It's part of the world's strategic infrastructure. Think of the global semiconductor industry as a massive printing press for human intelligence. Every other tech company is busy writing the books, but ASML is the only company on Earth that knows how to build the press. Without it, the story of progress in AI, medicine, and computing doesn't slow down. It simply ends. ASML doesn't just make machines. They make the future possible.